Hello, pre-cal class. We're going to try something today that we have been doing with my Algebra 2 classes. And then I'm going to do a little video here to talk about what you're going to see in your notes today to go along with your notes. And what we're going to start off talking about today is conics. This is section 9.1 in the textbook, and we're going to do sections 1, 2, and 3 out of this section. So if we're talking about conics, let's draw us a picture here to start off with. And I think you'll find this picture in your textbook in section 9.1 if you want to pull that out and look at it. But if we take a line and we rotate it about a point, and I didn't get my line very straight. Let me clear this and do this again. Let's make this go away and draw me a new set of conics. If I take my line and I rotate it about a point, then I end up with a set of stacked cones that look like this. That's what conics, where we're going to get our conics. And we call them conics because they come out of these two sets of cones. Well, conics are where we take a plane and we cut our cones. If I take a plane and I just cut right through my cone like this, well, what shape am I going to have? If I do that, I'm going to end up with a shape that looks like, if you look at it from the top down, you're going to end up with something that looks like a circle. All right, now, mine's a little lopsided, but, you know, I can't draw a straight circle when I do it on the board, so you're used to that. So there's my circle. And I got that by taking a plane and cutting through my cone. What other shapes can I get by cutting my cone? Well, what if I don't? We're going to go straight across. What if I go at slightly an angle? I run my plane through this way. Well, if I angle it just a little bit, then I end up with what really should be lopsided. I end up with a shape that looks like this. And that shape is known as an ellipse. You may have learned it as an oval in elementary school, but in mathematics it's called an ellipse. Okay, what else could I do? Well, I could, instead of going just slightly at an angle, I could cut through here parallel to one of my lines. Well, what happens? What shape do I have here when I take this plane and totally chop this section off? Well, depending on which direction my cones are turned, I could end up with something that looks like this, or it could be upside down, or it could be sideways like this. And we've dealt with these when we've dealt with quadratics. That's a parabola. And as a general rule, we deal with parabolas that open up or down. But in this section, we'll actually start looking at a few of them that open left and right. And then we have one other possibility. What if we come straight up and down? Well, if I come straight up and down, how many times do I intersect my cones? I intersect them twice. I intersect this top cone and I intersect this bottom cone, which means I can end up with a shape that looks like this. Like I have two parabolas back to back, or if I turn my cones sideways, I end up with two that go this direction. And that shape, where you have two of those, has a name. It's called a hyperbola, or hyperbola. All right. Well, these can all be described with equations. And we're used to looking at equations. We're used to looking at equations for parabolas. We know that they're quadratics. And we know that if we have something that looks like this, we might describe that with y equals x squared. Well, if it opens up or it opens down, then the x is squared. If it opens to the left or the right, the y is squared. But never are both of them squared. We have done lots and lots of equations where that x was a squared term, the y wasn't. Well, in this section, we might see some where the y is actually squared. But what about about the rest of these? Well, if I have an equation where x and y are both squared, I have x squared and y squared in my equation, and they have identical coefficients, they both have the same coefficient, then I'm going to end up with a circle. Now, what happened to the words here? X and y are squared. I lost my pen. I think I've lost my pen here. So let's see if I can draw this here. X and y are both squared. Alright, got my pen back. So we've already talked about the parabola, and either x or y is squared. The circle occurs where x and y are squared and they have the same coefficients. When I look at the equation for an ellipse, the x and the y are both squared, and they have different coefficients, but they're both the same sign. With the hyperbola, they're both squared, they have different coefficients, they have different signs. Now, what do I mean by that? Well, let's look at what these equations are going to look like. If I've got a circle, my equation might look something like x squared plus y squared equals 7. I'm saying that the x is squared, the y is squared, they both have the same coefficient. They both have a 1. Now, that coefficient could be anything. You know, I could have a 7 here and I could have a 7 over here. It doesn't really matter as long as they have exactly the same coefficient. Well, you're used to seeing a parabola. You know what a parabola looks like. You know, if I have y equals 3x squared plus 2x plus 4, then I have a parabola. What do I have? I have this x is squared, but the y is not. If that situation were reversed and the y were squared, then I would have a parabola that opened to the side. Well, what about these two new figures? This ellipse. In an ellipse, they're both squared. They have different coefficients, but the same sign. So I might have something that looks like x squared plus 9y squared equals 24. Both of these are squared. The coefficients are different, but they're both positive. This would be the same if they were both negative. They both have to have exactly the same sign. With the hyperbola, they're both squared, but one of them is negative. I could have x squared minus 3y squared is equal to 20. I've got both terms squared, different coefficients, and different signs. The x squared is positive, and the y squared is negative. So over these next 3 units, we're going to look at all 4 of these conic sections. Now, there are some other conic sections, but they are called degenerate conic sections. They get you something that's a little bit weird. For example, I could just draw, I get to land my plane right through this point where those two cones intersect. And what would be the only thing I would get from the cone? It would be a point. I could run it right down where it was just barely tangent to the cones, and I would get a line. Or I could run it so that I had 2 intersecting lines if I ran my plane straight up and down facing me, and then I would get this line and I would get this line. But those are called degenerate conic sections, and we don't usually refer to them as being conic sections. All right, so let's look at the first couple of the conic sections tonight. Let's look first of all at our circle. So let's clear our screen here and talk about what the equation looks like when we're dealing with a circle. You know me, I draw kind of lopsided circles, but we'll do the best we can here. Try and make this as close to being a circle as we can. Circle has a center, and then the distance that runs from the center to the circle itself we refer to as the radius. The equation for a circle is given as x minus h squared plus y minus k squared is equal to r squared. Now, what you need to know there is that hk is the center of your circle, and r is the length of your radius. Now, please pay attention. This is r squared. It's going to make us a difference in a minute. So, if I want the equation of a circle that has a center at 4, -7 and has a radius of 5, then I can simply write this equation as x minus 4 squared. H, it's the x part of the center, plus y minus a -7 squared, y part of the center, is equal to 5 squared. And more often than not, I would simplify that equation, and I would write this as x minus 4 quantity squared plus y plus 7 quantity squared is equal to 25. So if you're given this equation and you're asked what's the center of the circle? 4, -7, because there's a minus in this formula. So 4, -7. And what's the radius of the circle? The square root of this number. The radius of the circle is 25. Now be aware, if the center of this circle is at the origin, if it's at 0, 0, then the format is generally written as x squared plus y squared is equal to your radius squared. We don't generally put those zeros in for h and k. So just be aware of that you're probably not going to put a 0 if your center is at the origin on your circle. So the equation for a circle, pretty simple. Equation for a parabola, you've actually already done lots of work with, but we're going to talk about it in a slightly different context than we talked about it before, because we're going to introduce a couple of new terms. When we talk about a circle, we're talking about all the points that are exactly the same distance from the center. When we're talking about a parabola, something we have not discussed before is that the vertex of this parabola gives us what's called a locus of points, a set of points. So my set of points are those points that are the same distance from a single point called the focus and a line called the directrix. Remember when we talk about distance to a line, you'll remember from geometry, we're talking about perpendicular distance. But any place on this, the distance from the focus to the vertex is the same as the distance from the directrix to the vertex. A couple of things you need to know before we write an equation. The letter P is used to mean the distance from the focus to the vertex, or since they're exactly the same, or the vertex to the directrix. More often than not, it's referred to as focus to vertex because you're talking about 2 points and you don't have to get into that perpendicular distance stuff. If the equation gives you a parabola that is vertical, the ones that we're used to that open up or down, they either look like a smiley face or they look like a frowny face, then the equation for a parabola in conic section form is given as x minus h squared is equal to 4p y minus k. And remember we said p is this distance from the focus to the vertex. This hk is just like it is with a circle. It is the vertex of my parabola. Now, here's what we haven't done before. If it's horizontal, that means this opens to the left or opens to the right. It looks like this or it looks like this. And my equation is y minus k squared is equal to 4p times x minus h. Notice your x is not squared anymore. It's your y that's squared. So if I tell you that I have a parabola that has a vertex at the point 2, 3, and has a focus at the point 2, 5, can we find the equation for this parabola? Well, sure we can. Well, what are h and k? H and k are the vertex. So in this case, h is equal to 2, and k is equal to 3. We're getting that right from our vertex. Well, what about p? P is the distance from the vertex to the focus. So we have this distance from 3 to 5. So p here is equal to 5 minus 3. It's equal to 2. Well, is this a vertical parabola or is this a horizontal parabola? Well, if my vertex, let's pretend like this was at 2, 3. If my vertex is at 2, 3 and my focus is at 2, 5, it's above that. So if it's above, we're opening up or down, which means that this is a vertical parabola. So we're going to use this equation. So my equation is simply x minus, what's the h, what's the x part of my vertex, 2 squared is equal to 4 times p, which is 2, times y minus 3, the y part of my vertex. And you can simplify this 4 times 2 or not simplify this 4 times 2, whichever way you want to look at it. That's how we do parabolas when they are conic sections. In the next section, we will look at how to do an ellipse.